Fortunately, we don't need to worry about that. I missed what was just said.
Huzzah.
Ah, indeed. Questions? All right, so that brings us to this. Should have done the other right angle clamps because it requires less coordination. That was sad. All right, so I want those to be lined up. Oh, actually, I want them lined up. It should be over here. All right, so we're going to establish a pendulum here. So I take this and I pull this back, stabilize it a little bit, and when I let go, the question is, where does this bar need to be so that this will just barely make it over? If I put it down lower, and let go, it wraps around several times. And if I make it too high, and just coincidentally happen to hit almost where it's supposed to be, if it's too high, then it's just not going to quite get there. So the question is, where does this need to be so it just barely makes it over?
Halfway.
It's not halfway.
Interesting.
All right, so this involves, eventually involves a lot of stuff we've done already. So we have all this potential energy right here. We let go, recognize the forces acting on it. We have the force of gravity acting down. We have the tension in the string. What is the work done by the tension in the string as it's falling down to here?
Zero.
Why?
It's perpendicular to the conservative working force.
Oh,
It's perpendicular to the direction of motion.
yes. So we can now then figure out how fast this thing is going at the bottom. Once it starts to wrap itself around, we now have some work being done by the tension, thus it's going to speed up some. But let's go through that, come up with our prediction, and then we can test it out. I tried this as a lab a couple of years ago, failed miserably. All right, so our parts here, so we have the rod right here, our mass right here. This is length L. The distance from here to where the second bar is, D, and just to keep it straight and match along with my notes. So D. And I know that D is less than L. Otherwise, it's just a pendulum. And what I'm trying to find here is the ratio of D to L so that the mass just barely makes it over. So let's start out with, let's see. I'm going to correct one thing I said here. Once it gets to this point right here, it's still traveling in as part of a circular path, so the tension is still not doing work. All right, so let's just start out with the bottom. Just a little practice right there. What is the energy at this point? Or how fast is it going at this point?
Square root of 2GH.
Yeah. So we've all this energy at the top. We can be more specific than just H. We start out with all the energy at the top. It's all gravitational potential, and then we let go. It gets converted into kinetic. So I know E initial equals E final. Let's make this H is equal to 0. Sorry for those who are fans of H is equal to 0 at the top. We've gone through this process a couple times already, but we end up with mgh initial equals equals 1/2 mv final squared. So v at the bottom, let's call this point 1 right here. So I'm gonna call this v1 square root of 2gh. Except what is h in reference to the stuff that I've given here?
D.
What's
Nope.
D plus some number?
Oh, L.
L, yeah,
Oh, it is
that's
L.
the difference between this spot right here where it's perfectly level with it and that right there. Distance is L, so this is the square root of 2gl. Now, as it goes wrapping around here, again, it's traveling as part of an arc here. What is it, how fast is it going at this point?
Oh, it's square root of 2G L minus D.
At what point does this become a projectile motion problem?
When you lose tension?
So it still has tension at this point right here, but there's going to be some point in which there's slack in the rope, the tension is gone, it's now a projectile motion problem. We don't know exactly what that angle is at that point. We'll call this point 3. But we're going to say there is some angle here at which the angle at which tension goes to 0. At this point right here, for contrast, I use blue. Let's see if that does anything.
Reflecting.
All right, so the length here of this is L minus D. No, wait, sorry. Yeah, no, that's right, L minus D. And so my height at this point, well, the distance from there to there,
There's L minus D. Well, the quantity L minus D sine theta.
yes. And so at point 3, my height is, well, 0 is down there. L minus D gets me to here, then plus L minus D sine theta, which is just, so this is L minus D times 1 plus sine theta. And so my speed from an energy point of view becomes the square root of 2g L minus D 1 plus sine theta. And quick check of the notes to see how far astray we've gone. did some substitution at that point. Let me think through this just to make sure. All right, so that whole distance length of there is L, that is D, so that has to be L minus D. That's the radius of that turn right there. And so we end up with so if that's height 0, so it would be the square root of 2g times whatever the height is. All right, I'm good so far. We have one other aspect here at this point right here. At that, while the tension is acting on it, what can you describe about the path of the stopper?
It's
Still circular.
And if it's circular, what kind of problem are we dealing with?
So they,
I don't know. Rotational motion? I don't know.
We can be more specific than just rotational.
Circular motion, angular motion.
What's the magic physics word?
Centripetal.
That's the one. It's a centrifugal problem. So at that point right there, I know that the force is equal to mv squared over r. What is the centripetal force? What's causing it to travel in a circle?
The force of tension. Tension force?
Because that's what's acting in that direction. Let me do a quick check here. The reason why I'm getting all paranoid here is the fact that I don't want to get to a certain point later on where suddenly I'm going, oh, we left the minus sign off. H minus d sin theta, good, yada, yada, yada. Oh. Let's back up a second here. You know, the lesson here is I should listen to my gut if something was off. At the point when, at this point right here, this is the angle at which the tension goes to 0, what's causing the centripetal force?
Nothing.
Pardon?
Nothing?
No, there is no centripetal motion?
Well, it's parabolic, isn't it?
Not at this point. This is the point where it's transitioning from circular to parabolic.
Okay.
no.
What are the forces acting on it at this point?
Tension, you still have gravity.
Pardon?
I said you still have tension, and the only other one on there is gravity. So it's gravity.
But the tension is going off to 0 at that point.
Okay, so it's only gravity.
Or
The force due to gravity.
at that point right there, get rid of that. At that point right there, my weight is acting down. It is the component of the weight in that direction. Let's draw that a little bit bigger. Here's my weight. It's the component of the weight that is along the line of the string here, which is the centripetal force. This angle here is theta. The question is, which one of these is theta?
Oh.
See, that one's theta?
Yeah. No, the other one.
This one is theta? And fight.
Oh, yeah,
We-
because yeah, that's right.
We've gone through the same process of thing going down ramp. That one's theta.
Yeah.
So this is W sine theta. So what we end up with here is mg sine theta is equal to mv squared over r. M's cancel out. So we have another formula for v. That's equal to the radius, which is L minus D, times G, times the sine of theta, square root. Just because I hate writing this stuff over and over again. No, we'll leave it as is. So what I want to do is I want to solve for D as a function of theta. So I'm just going to set these two things equal to each other. So I have the square root of 2g L minus D 1 plus sine theta equals the square root of L minus D G sine theta. Square both sides. And then our D's disappear. Something's screwy here.
With two different functions, two different equations for velocity.
Speed. All right, so let's go back to, so that's 0. Pardon? Here? The radius, that's this bit right here. All right, something's. All right, so that's h is equal to 0. This would be, that's L, that's D. This would be L minus D, which is the length of this right here. So that's L minus D. That's L minus D sine theta. So this is L minus D sine theta. And so the height at this point would be that plus that. L minus D plus L minus D sine theta. Okay. Except I'm solving for D, so I don't want to cancel that term out. It's the height. Oh.
Isn't that what cancel?
If I square both sides, then I have a common factor. The problem is, yeah. That this is not right here. And consequently, this is not right. That's the problem. All right, let's go back to some basics here. At this point right here, we have energy initial equals energy final. We have mgh initial is equal to 1/2 mv2 squared plus mgh2. 2. So this becomes 1/2 mv, the m cancels out. So 1/2 v2 squared is equal to gh initial minus gh2. V2 would be the square root of 2g h initial minus h2, which is L minus D. So this is the square root of 2gd. here, this becomes the square root of 2GL minus that. Which is, we'll just take it from this form up here. That's L minus D plus L sine theta minus D sine theta. So that's this part right here. Sorry about that. So this becomes the square root of 2G, the L's will cancel out. And I'm left with D minus L sine theta plus D sine theta. All right, now we square both sides. 2GD minus 2GL sine theta plus 2GD sine theta equals LG sine theta minus DG sine theta. I think I distributed correctly. Again, we're solving for D in terms of theta. What's that theta right there? So let's get all the D's over on the left-hand side, everything else on the right-hand side. So I'm left with 2GD plus 2GD sine theta plus DG sine theta equals, so bringing that over to the left, and then bringing this over to the right, LG sine theta plus 2GL sine theta. This right here is 3GL sine theta. And this side over here would be D times 2G plus 3G sine theta. G will cancel out. And so now we have this value, this formula for the distance there to be no, not G. All right. This is not the final answer, because we still have this mysterious theta here. This is the point at which it is now a projectile motion problem. This is when the tension has gone away. And so now it goes into parabolic motion, and we wanted to just barely make it over. Questions to hear?
So, what went wrong with the height the first time? Why did it change?
We stuck in the height h here when this value really should be that minus wherever it happens to be. That was the problem. Yeah, so that's not right. Other questions? All right, we need some room here, so we've got that. I'm just going to write that off to the side. So D is equal to 3L sine theta over 2 plus 3 sine theta. And now let's just do some mess of erasing. Our energy bit is done. And it's now a projectile motion problem. This thing is shooting off at some angle here. And I need it to land here. Let's establish a coordinate system. IJ. The initial speed, V. Which speed do we end up using? That was one of the equations we erased there. So V is, what was the simpler one? There it is. L minus D, square root of L minus D, G sine theta. All right. I'll come back to that. All right, I know this angle here is theta, which means that either that's gonna be theta or that's gonna be theta. Drawing that out again, we have this angle theta here. V is there. Is that theta or is that theta? This one?
Yeah.
So let's go through the geometry. If this one's theta,
Yeah.
that angle right there has to be theta also. Which means this angle right here has to be the complement of theta. So that indeed would be theta there. So if we break it into I and j components here, delta x, vi, df, a, and t. I just chose up to be positive. So my initial speed horizontally is v sine theta. Vertically, v cosine theta. My acceleration horizontally, 0. Vertically, negative g. Displacement. What is the displacement?
Oh no, at that point,
This distance here is L minus D from here to here.
so you have L minus D cosine theta, L minus D sine theta.
So what's my horizontal displacement?
L minus D cosine theta.
And my vertical?
L minus D sine theta.
Close.
That makes sense.
What is the vertical displacement?
Oh, it's.
LD sine theta.
That's-
Minus D.
No. No.
Is it not that right there?
It's L minus D plus L minus D sine theta.
All right, it's going from this height right here to this height right here.
Half.
No, not half.
So L minus D minus L D sine
Right.
theta.
Say it again.
L minus D minus L minus D sine theta.
That would be this height.
L minus D sine theta minus L minus D.
Going way complicated here. From here to here.
L minus D sine.
Did somebody just say it? No.
Is it just D?
Nick was really close when he first said L minus D sine theta.
Negative L minus D sine theta?
Yes. Don't know the final speeds, final velocities. Well, I mean, no acceleration, so that's gonna be the same, but it doesn't really help us at all.
So don't.
Except, we don't explicitly need time, however, we do need to use the formula that has time in it. Since final velocity is the thing that we care about the least here, let's go into the cake formula. Delta x equals VIT plus 1/2 AT squared. So we have L minus D cosine theta, this is, we're doing obviously the I equation here, is equal to V sine theta time plus 0. And the J equation, we have negative L, we have D minus L sine theta equals V cosine theta times time.
plus 1/2 g, oh, sorry, minus 1/2 gt squared. And so now, we just need to combine them. It's probably simplest to solve for time,
Probably I, is the solve for time.
and then solve for time in one and plug into the other.
Well, I would like to solve for time for I.
First time I did it, I solved for time in this equation, still came out to the right answer, but
It's a lot.
it is a lot more complicated.
Yeah, because we need like at least 3 boards.
So L minus D cosine theta over V sine theta equals time. Pop that into the other one, and so we now have probably not enough room here, but let's do it, start it anyway. So D minus L sine theta equals and this is a huge mess. But we can persevere. So first off, we can get rid of speed here. Again, highlighting black on black there. There we go. Let's see, what are we solving for here?
I don't even know anymore. Or solve for time. No.
We did solve for time in one, we plugged into the other.
What are we solving for?
We're trying to find theta.
Oh yeah, theta. Solving for theta.
We were in, we're solving for time. Well, no.
Solve for sine theta, because we have sine theta over here.
Sure. So it's all that over D minus.
So I have D minus L sine theta. Right, just to cut down on some of the writing that we're doing here. I'm gonna let S equal sine theta, C equal cosine theta. And so we have D minus L times sine theta equals L minus D